you intuitively know how important it is to get fast responses. If you make users wait, they will bounce off your site faster than a kangaroo on a trampoline. However, there are so many things we can do to improve the performance of our API. So, to not waste your time, we will discuss only the things that we consider the most effective, meaning the things that require the least amount of effort to implement, but which would provide the greatest performance benefit. We'll start off with HTTP compression. When done right, data compression can result in a response time that is several times faster compared to an uncompressed response. But how can we determine how much faster is the response? That depends on the compression ratio. For instance, when the response we send is text-based, such as JSON, XML, HTML, or plain text, then compression can reduce the size of the data up to 10 times. This basically means that it will make the response time 10 times faster if we don't consider the time for setting up the connection, but this will be negligible anyway when working with large files. Binary files, such as images or videos, could also benefit from HTTP compression, but not as much as the text files, since binary files are usually already compressed. Still, applying compression at the HTTP level can still reduce the response time to half. Next, when should we use HTTP compression? When the API clients are connected over high latency connections, such as long distance connections or even satellite connections, then a lifesaver would be the HTTP compression. Sure, if you can afford servers in multiple locations, then you won't have latency problems. But if you don't want to spend money on extra servers, then you should be really careful with the size of the file that you send over the network, as it will really make a difference. Another use case for when the compression is especially beneficial is when you have data that is frequently changing. In this case, we can't really profit from a caching mechanism, as it's basically worthless. So, we need to make use of compression to significantly reduce the data transfer in such a system. Last but not least, if you have to transfer large text files, then compression will provide a substantial benefit. The bigger the file, the more pronounced the benefit. The only drawback of compression is that it requires more CPU resources. If your API server has limited processing power but has generous network bandwidth, then enabling compression may not be the best choice. Let's see quickly which are the steps to implement compression at HTTP level on the server but also on the client. We'll start with the server side or the API provider. First, we have to enable compression on the server. Most popular web servers or server-side frameworks provide built-in features or plugins to enable compression. So all we need to do is to enable it. For instance, for Nginx, it can look like this. You need to consult the documentation that is specific to your server framework or web server to learn how to enable compression. Then, we should set the appropriate HTTP headers. When responding to API requests, we need to include the appropriate HTTP headers to indicate that the compression is enabled. Here we have the content encoding header, which should specify the compression algorithm being used, such as gzip or deflate. These two algorithms are widely supported by most HTTP clients. Then, on the client side or API consumer, we need to include an accept encoding header in the HTTP request to indicate the client preference for compressed or uncompressed responses. For example, the client can set accept encoding gzip deflate if it supports compression, or omit the header if it prefers uncompressed responses. Afterward, the client needs to handle decompression to extract the original response data. If the client is a browser, then this is handled automatically. But if the client is an application, then you have to instruct the HTTP client libraries or frameworks you use to automatically handle the compression. With caching, your API responses are faster than a caffeinated cheetah since the requests are already processed and ready to be served. With caching, responses from server are temporarily stored and reused. In addition to the performance benefit, caching will also reduce the need for redundant data retrieval from the server. Caching, it's like giving your server a spa day so it doesn't get stressed out handling the same requests over and over. Now, caching can be implemented at any level of the interaction, but since we are talking about REST APIs, we are going to see how caching can be achieved only by using some HTTP logic. The advantage of this type of caching is that we don't need additional systems like caching servers, since the response would be stored on the client. Here, the client can be a web server or an application. Then, client would go and ask if the local copy he has is the most recent. If that specific resource hasn't been updated, then the server would respond with HTTP 304 not modified. So, the client can continue to use its local cached copy. Although this kind of conditional requests are invoked across the network, unmodified resources will result in an empty response body, thus saving the time and hardware necessary for transferring the resource back to the end client. Now, let's see which are the steps involved in implementing a cache mechanism on the server side. First, we need to identify cacheable resources or endpoints in our REST API. Which are the ones that can benefit from our caching? Typically, resources that don't change very much are good candidates for caching. Static resources are ideal for this. Second, we need to set the cache control header in the API responses. The cache control header is the most important header to set as it basically switches on caching on the clients. Without this header, the browser will request again the file on each subsequent request. If set to public, then resources can be cached not only by the end user browser, but also by any intermediate proxies. If set to private, then resources are not taken into consideration by middle proxies and can only be cached by the end clients. Additionally, we can also include the maximum amount of time a resource can be cached before considered out of date. For example, max age of 1 year in seconds would look like this. Finally, we need to choose a caching strategy based on our preferences. Here, we can use the last modified header to decide whether a resource is still valid or not. This is time-based expiration strategy. Or we can use an e-tag, which is basically a digest or a hash of the real content. Then we do the validation based on the content. Now, let's discuss what we should do if we are on the client side. Let's say that the client makes a request for a resource for its first time. So that resource is not yet cached locally. When we get the response from the server, we should first inspect the cache control header to know if the response can be cached and for how long. In this case, the client will store the resource, a document file, in the local cache for subsequent requests. Additionally, the server can provide some headers which are really helpful for the client to let him determine if a resource have changed since the last request. For example, last modified header or the e-tag header. The client will also store this information to use it later. Second step is to use these headers as conditional requests. After a while, the client might request again the same document. But now he can use the conditional request to check whether the resource was updated since the last call. If the server supports time-based expiration, then we can use if modified since header to validate the resource. This allows the server to respond with 304 not modified status if the cached version is still valid. Similarly, if the server supports content-based validation, then we can use if non-match header together with an e-tag to validate if the resource has been changed. Again, the server responds with 304 not modified, so we can use the value from the local cache. This helps a lot to reduce network latency and server load. However, if the server responds with something different than 304, for example with a 200 success, then we need to process the response and store it locally and reuse it for subsequent requests. Rate limiting for a REST API is putting limits on how many requests a client can make in a certain amount of time. A rate limiter is like a bouncer at a club. It's there to keep things under control. But how can it help with performance? When a server is getting overloaded and running out of resources, it can become slow or even unstable. Nobody likes a flaky API server. With rate limiting, you can prevent this kind of situations. Since the number of requests is under our control, we can make guarantees for service quality. For example, we can guarantee a certain response time for each request, or we can guarantee that the client can make at least a certain number of requests per unit of time. Also, you want to provide fair performance for each of your clients, right? If a specific client makes a large number of requests, it might monopolize the service and affect the performance of other clients. But rate limiting can help with that by treating everyone equally so that you can ensure a consistent level of service for all of your users. To implement a rate limiter on the server side, we need to do the following steps. First, we need to define the rules. Here, we define the criteria for rate limiting, such as maximum number of requests allowed per client, per endpoint, or per time window. Next, we choose a rate limiting algorithm. You should select a rate limiting algorithm that suits your requirements, such as token bucket or sliding window. Each algorithm has its own trade-offs in terms of accuracy, memory usage, and ease of implementation. We discuss them in detail in the rate limiting video. Next, we need to track and store request metrics. For each client, we need to keep track of some metrics. For example, the number of requests made and the timestamp of the last request. We store this information in a data store, such as a cache or a database. Finally, we enforce the rate limits. Before processing each incoming request, we check the request metrics for the client and we verify if it exceeds the defined rate limit rules. If the limit is exceeded, then we respond with an appropriate HTTP status code, for example 429 too many requests, or we implement a custom error response. Now, let's move on the client side. First, the user client should respect the HTTP status code it receives and, if there are, the rate limiting headers as well. Besides the status code, the server may provide additional rate limiting information in the response headers. For example, the maximum number of requests per time window, the remaining requests within the same time window, and the reset timestamp. The second step is to have a backoff strategy. When the client receives a rate limit response, for example HTTP status code 429, it should handle it gracefully. A retry logic can be implemented here while respecting the header called retried after if it is provided by the server. Asynchronous requests can significantly improve throughput and scalability. When multiple requests can be processed at the same time without waiting for each other, our application would be much more efficient. Therefore, it could handle a higher volume of incoming requests. In this e-commerce website example, we see that in the synchronous method, the user is waiting for the first response of the request and he can't make a new request. While in the async method, the user can make other requests while waiting for the first request. In this async system, it looks like the requests are processed in parallel, although technically they are not, since only one thread is involved usually. The end result is a much faster processing time. But why is this difference? For this, let's zoom in the e-commerce website that is synchronous. An e-commerce website normally has a shopping cart feature. When a user adds items to their cart and proceeds to the checkout, the website needs to do several things. To calculate the total price, to apply discounts if there are promotions, and to do inventory checks, and all this for each item in the cart. Let's say that these functionalities are implemented by separate services. In a synchronous method, we can execute these three operations in two ways. We can choose to do it sequential, which means that the caller waits for the response before moving on to the next request. This is quite bad because we have to wait for the previous action before we move to the next. The other option is to do it in parallel. Here, we'll need to fire up multiple threads and then manage them. This is not ideal because managing a large number of threads can consume a significant amount of memory and CPU resources. Multiple threads in parallel is an efficient way of working when doing intensive computation tasks like cryptocurrency mining or machine learning. In those cases, we can actually leverage the processing power. However, when waiting idle for responses that should come over the network, it's much more efficient to use async communication. Now, let's see how this would work in an asynchronous approach. For each item the user adds in the cart, we make asynchronous HTTP requests to do calculation and inventory checks. We do this simultaneously without waiting for each response. Here's what happens. Concurrent requests are made to the pricing and inventory services for each item in the cart. We see that the website doesn't wait for any specific response to come back and continues to provide a responsive user interface. As the responses arrive, the website updates the cart total price and inventory status for each item. When it comes to serialization, JSON and XML are the most popular and supported across all programming languages and platforms. Quick reminder: serialization is the process of transforming application objects like the ones from Java or Python into JSON or XML file formats with the purpose of being stored or transferred over the network. Deserialization is the opposite process where the file representation would be transformed in an application object. The issue with the JSON and XML formats is that they are not the most efficient way of encoding. When it comes to performance, protocol buffers generally outperforms JSON and XML in terms of serialization and deserialization speed and the message size. Due to its binary format and efficient encoding, protocol buffers can significantly reduce the size of the payload and therefore improve the network transfer speed. In some way, protocol buffers is similar to HTTP compression, as they both significantly reduce the size of text-based formats. However, compression doesn't address the inherent inefficiencies of those formats. Protocol buffers is treating this at the source. Still, if you value more being compatible with existing systems or the human readability, then the text formats with compression can still be a workable option. Now, let's see how we can send some data between two applications using the protocol buffers. On the server side, we need to do the following steps. First, define the protocol buffer schema. We do this by creating a proto file where we define the message types and their fields using the protocol buffers language syntax. This schema will serve as the contract between the clients and the server. The most uncommon elements of the proto files are the numbers assigned to each entity of the message. These dedicated numbers make each attribute unique and are used to identify the assigned fields in the binary encoded output. Next, we will use this person proto file we created to generate code in the desired programming language. In our case, we want to generate Python-specific code. So, we need to use the proto compiler, proto-c, and give it as parameter python-out to generate Python-specific code, and we also specify the proto file that will be compiled. The code will generate classes and structures that will represent the defined message types and will handle serialization and deserialization. Next, in our code, we want to serialize the data we want to send over the network. We use the generated code to create and send the protocol buffer messages. Then we create a dummy object, and then for the REST API, it often involves serializing messages to binary format and sending them as request or response content. Finally, we set the appropriate content type header. This is to express that the response data is in protocol buffers format. The common content type is application/x-protobuf. On the client side, the procedure is similar. First, we'll use the same person proto file to generate the client code in the desired programming language. We'll use again the protocol buffers compiler proto-c. Then, we set the appropriate accept header. This is to express that the response data is in protocol buffers format. Finally, we deserialize the response data. When the client receives a response from the REST API, it can use the generated code to deserialize the binary protocol buffers data into the corresponding message object. Now, we can access the response data to retrieve the desired data. The client code will also provide accessors or properties for the fields in the protocol buffer schema. A request that might take a long time to process, such as a complex calculation or bulk processing, should be performed without blocking the client that submitted the request. If we make the clients wait for the response, then several unwanted things might happen. First, this can reduce scalability because of poor resource utilization. Longer timeouts increase the time a request can hold resources, leading to decreased performance and resource utilization both on the server and the client. If a large number of requests with long timeouts are waiting for responses, it can lead to resource exhaustion and reduced scalability. For instance, this can lead to connection pool saturation. Most web servers have a limited number of allowed connections. Long timeouts can cause connection pools to be occupied for extended periods, limiting the availability of connections for other incoming requests. This can result in connection pool exhaustion and prevent new requests from being processed. Let's see a simple example. Imagine we have a dataset that we want to give to a server and we want in return some calculation done, like the mean, median, minimum, and maximum. Let's imagine that this is a long-running process. How do we provide asynchronous support for this request using REST endpoints? For this, we can return HTTP status 202 accepted to indicate that the request was accepted for processing but is not completed. The Web API can perform some initial checking to validate the request and then initiate a separate task to perform the work and return a response message with HTTP code 202 accepted. Basically, we offload the request to a background task. In addition to the post endpoint, we should also expose an endpoint that returns the status of the asynchronous request so that the client can monitor the status by pulling the progress at regular intervals of time. When the progress status shows done, we can go ahead and check again the initial endpoint for the results. A common question is what is considered a long response time. The processing time for long-running processes can range from seconds to hours or even days, depending on the specifics of the task. For any processing that takes more than a couple of seconds, we can implement it using the asynchronous mechanism we saw earlier.